Today we're going to talk about the Cauchy Riemann equations, which are the foundation of complex analysis, both from the pure side and from the applied side. So let me give you an outline of what we're going to do. We've got the Cauchy Riemann equations. Oops, sorry. We need to have a little review about limits because that's where this all comes from. We're going to talk about a bad limit. You might have seen this earlier in calculus, but just so you know that this is a possibility. Then we're going to talk about the good limits, and that'll be the Cauchy Riemann equations. And finally, a little bit about harmonic functions, which are so important in so many applications. And the partial differential equations of mathematical physics are based on the Laplace equation, which is what we're going to see here. So, without further ado, when we say limit, I'm not going to say this out loud just for a second. So here's a typical limits statement. Everyone in the universe says x goes to a. That's not true. X isn't going anywhere. X is near a. So this is limit for x near a of f of x. And so we're seeing what happens when x is near a. And if you go into the epsilon delta definition that you learned in real analysis, x is near a is equal to L. And let's write out that epsilon delta definition. That means for every epsilon, there exists a delta such that the following implication holds. Implication is a little bit flaky, but we're just going to go with it for now. So this is the exact definition of limit that you learned when you first learned about limits. For every epsilon greater than 0, there exists a delta, and the implication is that if x is near delta, if x is near a, then f of x is near epsilon. The only difference here is that this is the complex absolute value. It's the distance in the complex plane from x to a, and this is the complex absolute value. This is the distance in the complex plane from f of x to L. And just as a reminder, the complex absolute value comes from the conjugate I seem to have written it backwards. Okay. Well, you take the complex absolute value, you take z times its complex conjugate, and that's the distance squared. So I think I may have messed that up. Okay. You've seen this before, so that's not a worry. So let me write down a bad limit. This is a function of two variables, f of x, y. It's a fraction. And remember, when I talk about fractions, I say it's a fraction first before I say what the top and bottom are. The top is xy, and the bottom is x squared plus y squared. So these are ordinary real x and y, and there's an obvious problem at the origin because x squared plus y squared is 0. But every place else, this is just some number, and that's good, that's fine. What's interesting about this is if we look in the xy plane, and if we, this is why it's a little bit confusing sometimes. If we look at values that are on the x-axis, so those would look like x0, f of x0 is 0 because the top of this fraction is 0. And so the limit is 0. On the other hand, if we look along the diagonal where x is equal to y, so that would mean that the point has coordinates xx, f of xx is x squared over 2x squared, so that's a half. So along this horizontal, the limit's clearly 0. All the values are 0, so the best prediction is that the value at the origin would be 0. On the other hand, if you come along the diagonal, all the values are a half, so the best guess as to what would happen at the origin would be a half. Those don't agree. So this limit does not exist. And so that's the issue with limits in the plane. So let me just kind of make a quick note here limit for xy near 0, 0 of that fraction, xy on top, x squared plus y squared on the bottom, does not exist. So that's bad. Well, it's good. I mean, it just is what it is. Okay, so we want to work with the derivative, and the Cauchy Riemann's equations say that the derivative is a good limit. The derivative that you write down is, in fact, does exist, and the way the Cauchy Riemann equations come about is that you compare what happens when you move in horizontally with what happens when you move in vertically. The assumption is that those are the same, and that's where the equations come from. You get the same value for the limit in two different ways. So let's see what goes on here. We've got a function f of x plus iy, and the real part is u, and the imaginary part is v. So that gives us something like this. So u is the real part, v is the imaginary part. And what we're going to do is take the limit that would be the derivative. It's the same difference quotient that you learned back in 4th grade or something. And so what we're going to do is come in horizontally. So you're going to have f of x plus h comma y. I'm sorry, not comma. I'll change that, x plus h plus iy. I forgot we're being complex. And that is u of x plus h plus iy minus, plus iv of x plus h plus iy. Just writing in what we've done to the x variable. And then if we divide that by h, which I am going to do in retrospect, that now is going to be what's going into the difference quotient for the derivative. And what's going to happen is, you've done enough of these before, I assume you'll follow this. The u part will go to the partial derivative of u with respect to x, and the v part will go to the partial derivative of v with respect to x. There's a common notation for partial derivatives is to use subscripts. Otherwise, sometimes things get kind of funky. So you take this minus u of x plus iy over h, that's just the real part, and you're going to just get the partial derivative of u with respect to x, and then on the imaginary side, you're going to get the partial derivative of v with respect to x. So this is the derivative. Now we're going to do it coming along a different path, and we're going to have f of x plus iy plus ih. So now the variation is going to be in the vertical direction, or the imaginary direction, and so writing out what happens there, that is u of x plus iy plus ih plus I times v of x plus iy plus ih. So this is what would go into your derivative calculation. But now, if you take that by h, well, the thing is you've modified the input by ih, so you have to divide by ih. And so what you end up is that the derivative is equal to 1 over I times the partial of u with respect to y plus I times 1 over I times the partial of v with respect to I, because you've got IH, not H. And so this is minus I uy plus vy. And if you compare the two real parts, you get the first half of the Cauchy Riemann equation, which says that ux is vy. And if you compare the imaginary parts, you get the second part of the Cauchy Riemann equations. And that says, sorry, my screensaver started up. And that says, with the imaginary parts, that Vx is minus Uy. And those are the Cauchy Riemann equations. And so the interesting thing comes when you take second derivatives. So I'm just going to run this quick calculation by you here. If I look at the partial second derivative of u with respect to x, that's uxx. Well, by the Cauchy Riemann equations, that's vyx. And by continuity, that is vxy. And by the Cauchy Riemann equations, that is minus uyy. So there's that little calculation. This is continuity of the second partials. Uxx is where we started. We use the Cauchy Riemann equations. We use the continuity. We use the Cauchy Riemann equations again, and you find out that second derivative of u with respect to x is minus the second derivative of u with respect to y. So that is the Laplace equation. The second derivative of u with respect to x plus the second derivative of u with respect to y is 0, and that makes u a harmonic function. So there's lots of stuff in the textbook about this, but this is the basis for so many of the applications of mathematics, or this Laplace equation. That's important, so that's where we're going to end.